Hello, in this video, in the final video of this chapter, and actually the final video of Year 1 Mechanics, we're not really going to be looking at anything new per se, but we're going to be revisiting constant acceleration and revisiting our Suvat formulas here. So in the last chapter we looked at constant acceleration, so we said when the acceleration is the same throughout the journey, we can use these Suvat formulas to find missing displacements, missing velocities, or the time taken for some part of the journey, right? And so the key idea is, again, these Suvat formulas only work with constant acceleration. Okay? So that means the acceleration again has to be the same all throughout the whole journey, okay? When the acceleration varies, right, so throughout the time of the journey, the acceleration constantly changes, then we can't use them. And so instead, we use the techniques we've seen in this chapter. So we use functions, and we can use calculus, so differentiation and integration, to convert from displacement to velocity to acceleration, right? And then vice versa, okay? So we can't use Suvat formulas to solve problems we've seen in this chapter when it's variable acceleration, but actually we can use calculus, the techniques we've seen in this chapter, to go back and solve constant acceleration problems alternative to Suvat, okay? And actually the other thing we can do is actually we can derive or prove these Suvat formulas using calculus and functions instead, okay, which we've seen in this chapter, where previously we've seen how these formulas arise from the velocity time graph, and you do need to know how to derive these formulas from a velocity time graph. The question will be structured though. The question will give you a graph and you have something to work with, but you need to be able to be comfortable with answering questions involving deriving these formulas from a graph. But alternatively, we can derive them, these formulas, using calculus instead. Okay, so let's just jump into it then. So firstly, I've got this question here, and we're asked which of these equations for displacement describes constant acceleration. Explain your answer. Okay, so part A, we have the displacement S is 2t squared minus t cubed. Now it's asking about constant acceleration. Well, acceleration, but we've got displacement here, right? So remember, displacement, how are we going to get to acceleration from that? Well, we're going to differentiate, right? But differentiating displacement gets me velocity. So I'm going to need to differentiate again to get to acceleration, okay? So to consider the acceleration here, I need to differentiate. So the velocity then is going to be the derivative. So if I differentiate this, where 2t squared will go to 4t, then minus t cubed will go to minus 3t squared. Okay, then if I differentiate again, then I get the acceleration. So that's the derivative of velocity now. So if I differentiate this, well, 4t goes to 4, and then minus 3t squared goes to minus 6t. Now that's the acceleration. It's 4 minus 6t. Now, is that constant? So constant meaning does not involve t or variable. Okay, that's what constant means. It does not involve any variables, or just a single number. It's just a fixed number, right? But here, my acceleration is in terms of t, so it's not constant. So it involves t. So acceleration not constant. Okay, and there we are. Then for part B, we have S is 4t plus 7. So now if I quickly go to differentiate, well then the v, if I differentiate this then, well, 4t goes to 4, and then 7, the number, any number goes to 0 when it differentiates, so there we are. So the velocity is just 4 then if I differentiate. So then to get the acceleration, well, if I differentiate 4, that's just a number, so a goes to 0. And there we are. So that's saying now the acceleration is always 0, but it doesn't involve a t. So actually it is constant, it's just a fixed number, 0. So it does not involve t. So it is constant acceleration. And so there we are. Now in part C, we have f is t squared over 4. Or, to make it more nicer, this is a quarter t to the 4, t squared, sorry, this way. So if I differentiate then, I get the velocity. If I differentiate a quarter t squared, will that go to 2 over 4 or half t? And then if I differentiate again, then the acceleration is just a half. Well, again, it's fixed. It's a fixed number. There's no t involved, so it is a constant acceleration. Okay. Then in part D, we now have s is 3t minus 2 over t squared. So firstly, this fraction is going to cause a problem. I can't differentiate it. I need to convert it. That's just the power of t with no fractions. Okay. So if I rewrite this, this is 3t minus 2t to the minus 2. Okay. Remember, I can convert any fraction into a negative power like this. Now we're going to differentiate. So that means the velocity, well, 3t will go to 3, and minus 2t to the minus 2 would be plus 4t to the minus 3. Okay. Remember, we times by the power in the front, then we knock one off. Then the acceleration from that, if we differentiate, well, here, again, 3, here will go to 0. But that's just nothing. And then 4t to the minus 3 will go to minus 12t to the minus 4. Okay. Well, that now involves a t, so it's not constant. Okay. And there we are. Then lastly, in part E, we have s is 6. Okay. So actually, there is no t anyway with displacement. It's just 6. The number 6. So again, if we differentiate, well, differentiating a constant or something that isn't t, well, it just goes to 0. And so therefore 0 would also differentiate to 0. And there we are. So again, it's constant, right? Because it's a fixed number 0. So it's constant acceleration here. So that's the whole gist, okay? That is the whole gist of what we mean by constant acceleration. We can differentiate if we need to. And then if the acceleration does not involve a t, but just a fixed number, then it means it's constant, it's fixed, okay? So there we are. Now, I also said we can prove our Seebeck formulas using calculus that we've seen in this chapter. So what do I mean by this? Well, in this example, we're told a particle moves in a straight line with constant acceleration a, given that its initial velocity is u and the initial displacement is 0. Firstly, we need to prove that the velocity is v is u plus at. That's what we need to prove, okay? Now, hopefully that is a very familiar formula from the Seebeck equations, right? But how do we prove, how do we get to it? Well, the only information we can really start with is the fact we're given constant acceleration. If I call the acceleration a of t, so this is a function of deceleration, right, in terms of t, well, actually, the acceleration here, right, we're told the acceleration is constant, and I'm told it's equal to a then. So it's just equal to a. A is just a number. It does not involve a t. So this is constant, okay? So I can just call the acceleration a. So then, if I want the velocity, I'm going to need to integrate. So remember, from acceleration to velocity then, I'm going to need to integrate, right? Do not get confused. It's not differentiation, because velocity would differentiate to acceleration. But if we go the other way around, from acceleration to velocity, then it's the opposite, so integration. You can remember these links by recognizing the fact that they graph what their gradients mean. So with displacement, a displacement graph, velocity is the gradient. Hence, you differentiate displacement to get to velocity. And then with a velocity graph, the gradient is acceleration. So you differentiate velocity to get to acceleration, because differentiation is gradients. You can pick your way to remember the relationships here, but you do need to remember what differentiates or integrates into what. Okay. Okay, so we're going to need to integrate to velocity. So the integral of a then, right, dt. I'm integrating my acceleration with respect to time. Well, again, it's just a number, so just add a t on when we integrate. There's a t, and then plus my c, add a plus c. And so that's my velocity then, right? That's my velocity, at plus c. So hopefully you can recognise we're pretty much at the formula, but we just got this plus c, right? Well, actually, what we're given is that the initial velocity is u. So that means when t is 0, initially, the velocity is u. Okay? So if we sub that in, that means u is equal to a of 0 plus c. Therefore, c is u. Okay? And so therefore, by substituting c into here, v is at plus u. And if we rearrange that ever so slightly, we get v is u plus at. There we are, okay? So that's the idea. We can integrate or differentiate to get from one thing to another, and then we can get these formulas here. Okay, then in part B, now he wants to say that the displacement is given by this formula here. So now we have the velocity. So if we want the displacement, again, remember from velocity to displacement, I'm going to need to integrate again, right? So if I integrate the velocity, so it's the integral of u plus at dt, that's going to be, well, u is just a constant, right? So we'll just attach a t on. So it's going to be ut. Then at, well, that's going to be, if we add 1 to the power, so t has a power of 1, right? So we add 1 to that power, we get at squared, then we divide by the power, so 2. So a half, right? If we simplify it, and then we have another constant on, plus d, okay? And if we can simplify it ever so slightly, that'd be ut at a half at squared plus d. Okay, so that's s then, right? That's s, right? There. Okay, so we're nearly there, but again, we got this other constant we don't know, d here, right? The constant of integration. Well, again, we're told that the initial displacement is 0. So that means when t is 0, s is 0, right? So if we sub that in, that means 0 is going to be u lots of 0 at a half of a lots of 0 squared at d. Therefore, d is 0. D is 0, right? So therefore, we get that s is ut at a half at squared. And that is it, okay? The d goes away because it's 0. And there we are. We get the formula they wanted. S is ut at a half at squared. And there we are. So that's the whole idea. We can prove the formulas in the Suvat formulas in this way as well. Okay, but yeah, so that's the idea. We can prove the formulas this way as well. Started with the fact the acceleration will always be constant. Okay, so there we are. Okay, right. So we're going to look at some more questions, and I did say as well, we can solve some of the constant acceleration problems we've seen in, or the Suvat problems we've seen in the constant acceleration chapter. We can actually approach those same problems through the lens of calculus instead. Okay, so let's have a look at this example here. So we're told a particle moves in a straight line with constant acceleration. The initial velocity of the particle is 5 meters per second, and after 2 seconds, it's moving with velocity 13. So in part A, it wants me to find the acceleration of the particle. Now, probably there's two ways you can approach this now. The first way is the Suvat way, right? Which is probably the way I'd probably recommend still, right? And if you see constant acceleration mentioned, using Suvat probably isn't a bad idea. So if we were to approach this using Suvat, well, actually, we're told that, well, if I list my Suvat right, my displacement S, my U, initial velocity, V, my final velocity, A, the acceleration, and T for time. Well, I'm not told anything about displacement, I don't care about it, but I am told the initial velocity is 5. I'm told the final velocity is 13, and this is in 2 seconds. So I want to find the acceleration, okay? So that will invoke the formula V is U plus AT. Right, so remember, we've got these 5 Suvat formulas. We take the formula that does not involve the part we care about. So we don't want the formula with an S in, right? So so we sub that information in. So that means 13 is going to equal 5, add A lots of 2. So therefore 2A is going to be 8, so A is 4. And there we are. Now the other method we can approach this by is now by using our calculus method. So almost treating it like it's variable, right? In the exact same way we've been doing this whole chapter. So how are we going to approach to finding the acceleration this way? Well, actually, I'm going to start by calling the acceleration the function a of t, and I'm just going to call it a. Okay, again, because we're told the acceleration is constant, so the acceleration function is just going to equal the letter a. There's no t involved. So then, if we're given information about the velocities, then right, the velocity. Well, if I integrate then to get the velocity, that means v of t, the velocity function. If I integrate a dt, well, that's just a letter, so I attach a t onto it. So it's going to be at plus c. Now, to find the plus c, then, I'm going to use the information given, right? So firstly, I'm told the initial velocity is 5. That means when t is 0, because that's initially, that means v is then 5, right? So if I use t0, that means v is 5. If I sub that in, that means the velocity v of t, well, v is 5, so 5 is going to be equal to a lots of 0 plus c. Therefore, c is 0. No, 5, sorry. So, if this is my velocity function, then that means my velocity is at plus 5. There we are. Okay. Okay. But we need to find the acceleration a. That's what it's asking me to do, right? It's asking me to find the acceleration a. But I'm also given the information that after 2 seconds, its velocity is 13. That means when t is 2, v is 13. So if I use that information and sub that into the velocity function I've got, so t is 2, v is 15? No, 13. So that means 13... for v is going to equal a lots of 2 plus 5. So therefore we get the equation 2a is 8, and therefore a is 4. So that matches the acceleration we got via the Suvat way. Okay, and so there we are. So 2 different ways you can approach this question. Okay, then in part B, it kind of forces us to use a certain method. It says in part B now, without using the kinematics formula, so the Suvat formula, right? Show that the displacement is given by this expression here, okay? So we need to consider we need to find the displacement, but they told us we can't use the Suvat formula, so we're going to have to use the calculus approach. Okay, so again, we know that the velocity function is now 80 at 5, but we know that a is 4, so it's 40 at 5. So if I want the displacement then, so the displacement function is going to be the integral of velocity, so 40 at 5. So if I integrate that, well, 40 will go to 40 squared, then divide by the power 2. Then 5, we just add a t on. And then we add another constant plus d. Okay? But we need to find what this d is, right? This missing letter d. Well, firstly, I can simplify it, right? Because I can simplify the fraction. So s of t is 2t squared add 5t plus d. Now, there's also a hidden a sort of hidden implied condition that the initial displacement is 0, right? Because usually with these sort of problems, vast majority of the time, we start at the starting point, right? Hence why we call it the starting point, because we start there, so we're not displaced anywhere. So the implicit assumption is, if you're not given any information about any displacements, you can usually take that initially at t0, the starting displacement is 0, because it's at the starting point, right? So if I sub that information in, so if I sub in t0, s is 0 then, because the initially you've not moved anywhere, right? So that means that 0 is going to equal 2 lots of 0 squared, add 5 lots of 0, add d, therefore d is 0, okay? So therefore my final equation is s of t is 2t squared add 5t. And so that matches what I've got here. So that means p in q and r, okay, they're the coefficients, so p is going to be 2 there, q is going to be 5, and r, well, r goes to 0, right, there, okay, and so there we are, okay. Right, let's have a look at this question here, and the final part of the question can get a bit tricky, but let's have a look. So we're told here a train travels along a straight track, passing point A at time t0 and passing point B 40 seconds later. Its distance from A is given by S is 25t minus 0.2t squared. And for part A, he wants me to find the distance AB. So AB is the length from A to B, right? The distance from point A to point B. Now, we're given the distance formula, right? And we're told it reaches point B 40 seconds later. Well, actually, if it starts at A, well, actually, we could find the distance to point B by simply subbing in, right? Subbing t is 40, because then that would get me the length to B, right? So that means S is going to be 25 lots of 40, take away 0.2 of 40 squared. And so that will get me 680 meters. Okay, and so there we are. So if our starting point is A, then actually the displacement here to B, that's just the length from A to B, right? So there we are. So AB is 680 meters. Okay, there we are. Then in part B, it wants me to show that the train travels with constant acceleration. So that's very similar to what we did at the very start. So if we want to consider the acceleration, well, again, we've got displacement. So firstly, we're gonna have to differentiate the velocity. So velocity then, again, if I differentiate the displacement equation here, well, 25t will go to 25 when differentiated. Then minus 0.2t squared will go to minus 0.4t. And there we are. And so that's the velocity. Then if I differentiate again, I get the acceleration. So 25, the number goes to 0, but it goes away. And then minus 0.4t will go to minus 0.4. Well, there we are. It's constant. The acceleration is constant. It's just a fixed number. There's no t involved. So acceleration does not involve t. So it's constant. Right, and I say it's fixed at minus 0.4 meters per second. So that's the acceleration throughout the whole journey, minus 0.4 meters per second. There we are. Now in part C, this is where it gets interesting. So we're told here a bird passes point B. So by the way, this whole time we've just been talking about a train. Now it's talking about a bird now, and the bird passes point B at time t0. So now the bird is initially at point B now, okay, kind of at the other end, right? And it has initial velocity of 7 towards A, so it's going towards A. So the train, so if I draw this information, what's happening here? Again, draw a little diagram to really help with these sort of problems. So we start at the point A here and we end at B here. Now the train, God, if I do a very rubbish train, I don't know, something like that, right? This is my train. It starts at A. We're told it passes point A at t0. So initially at t0, it's at A. And then it goes to point B 40 seconds later. Okay. But anyway. Now the bird is now at point B. So if I draw little birds then, oh God, there, a bird, there we are. This is my bird. It now starts at point B, at the other end of the track, okay? So the bird is heading towards A, right? So its initial velocity is 7. So that means its velocity is going backwards by 7 meters per second. The acceleration of the bird is constant. It's 0.6. So it's 0.6, the acceleration of the bird here. There we are. And so in part C, wants me to find the distance from A at which the bird is directly above the train. So at some point here down the road, I don't know where that point is, the train, right, this train is going to be directly below the bird, okay, in this way. That's what's happening. So it wants me to find the distance from A. It wants me to find that distance from when, basically, they're both on top of one another, okay? Right. And that's really all the information we're given, really. So hopefully that diagram makes sense. That's what's going on here. Again, draw a little diagram to visualise the information if it's just so much going on, right? So hopefully the diagram breaks it down more simply. That's what's happening. So we want to find the distance from A, so where the train starts. We want to find the distance from when the two objects overlap. Well, actually, they're at the same point. So actually, the displacements have to be the same then, right? Of the two objects, the displacements have to be the exact same if they're at the same position, right? Okay. So actually, if we consider the displacement of the two objects, so firstly the train, right? The train. I want to find the displacement of the train. I'm going to call ST. Okay, S for train, right? I mean T for train. So I already have the displacement for the train. I'm given to it earlier on in the question, right? The displacement of the train is 25t. Take away 0.2t squared. And there we are. So that's great, but then the bird is a bit more complicated because I don't have a displacement formula for the bird, but I'm going to need to work one out. So then S of B, well, at the moment I don't know what the formula for the displacement of the bird is, but what I do know is that if I go back to my diagram, it has a constant acceleration of 0.6. Okay, so that means I can start from the acceleration. And hopefully you can start to see then how I can get to the displacement. So the acceleration of the bird is A is, well, if I'm treating forwards as positive, it's going backwards, right? The acceleration, the bird is moving backwards. So it's going in the negative direction. So actually the acceleration is minus 0.6. Okay. Now, if I want to get a formula for the displacement, firstly I'm going to have to get to displacement. I'm going to need to firstly get to velocity. To do that, I'm going to have to integrate, right? So then my velocity, well, if I integrate minus 0.6, that'll just be minus 0.6t. I'll just add a t on, and then my plus c, right? So that's integrating minus 0.6t. Okay, so, okay, I need to find this plus c. Well, actually, I'm also given, right, initially, the velocity of the bird is 7. And again, it's going in the negative direction, so the velocity would be minus 7. So actually, when t is 0, initially, v is minus 7, right? So if I sub that in, minus 7 is going to be minus 0.6, lots of 0 plus c. Therefore, c is minus 7. And so therefore, I get my complete equation for velocity here. And so then, to get to displacement, well, we need to integrate again, right? So the displacement S is going to be the integral of velocity. So integral of minus 0.6t minus 7 dt. So if we work that out, well, minus 0.6t will integrate to minus 0.6t squared. Then we divide by the power 2. And then minus 7, we just go to minus 7t. So we add a t onto it. And then we add on another constant plus d, right? So there we are. Now, then we need to find this plus d, this missing constant here. Okay, so we're going to need some sort of condition or value to sub into it. But if we look at the question explicitly, we're not given anything about any displacements of the bird, right? But actually, what we do know, okay, if we look at a diagram, again, we do know the bird starts at point B. Now, we're actually assuming, right, which is the displacements are measured from point A, right? So A is kind of like our starting point for all of this. But the bird initially is at point B. So actually, the displacement of the bird, so the distance from point A, well, is the distance from A to B. But actually, didn't we work out in part A what that distance was? The distance from the two ends, A to B. 680 metres, right? So that means the bird is 680 metres from A if it's at the point B, right? So that means initially for the bird, when t is 0, the displacement is 680. Then, right, because it's 680 meters from A, because that's where we're measuring our displacement from, okay? And it would be positive 680 because the bird is 680 meters in front of A, forwards, okay, in the positive direction. So the bird, yes, the bird is moving in the negative direction backwards, but in terms of distance, it's ahead of A. So the distance is positive, okay? So there we are, okay? So make sure you're comfortable with how we got those values, and particularly pay attention to the signs, okay? So hopefully they made sense. So that means when t is 0, S is 680. So that means if we sub that in, that means 680 is going to be, well, we can simplify this fraction. That would be minus 0.3. T squared, well, t squared is 0 squared, minus 7 lots of 0 add d, therefore d is 680. And so therefore we've got our full equation for displacement here, which is minus 0.3 t squared, minus 7t, add d, so add 680. And there we are. That is my displacement for the bird there. So actually now, we actually have now worked out a displacement formula or function for the bird, right? It's this minus 0.3 t squared minus 70 at 680, right? And there we are. So then, as we discussed then, if we want to find the distance here, right, until the point where the bird and the train overlap, or essentially they meet, they're at the same point, right? Well, again, if they're at the same point, then their displacements have to be equal, right? So that means when they meet, when the train and bird meet, their displacements are equal. So that means S of t equals S of b. So the train and the bird displacements are equal. Well, at that point then, that means we just equate these two expressions here then, right? So that means 25t minus 0.2t squared equals minus 0.3t squared minus 7t add 680, right? So there we are. And so at that point we just solve this quadratic, right? So if we add 0.3t squared to both sides, we get plus 0.1t squared. Then if we add 70, we get 32t, and then subtract 680 equal to 0. So then we solve this quadratic, so we can just plug it into the formula. So t is minus 32 plus or minus the root of 32 squared minus 4 lots of 0.1 lots of minus 680 over 2 lots of 0.1. And so if we put that in the calculator, we get t is 20, or t is minus 340. But of course we can't have negative time, so we can only accept the positive solution, so t is 20 seconds. So this is the time when the bird and the train meet at the same point, right? But they're not asked us for the time when they meet. They asked me for the distance, right? This distance here from the point A to when they meet. So actually that is just the displacement then, right? At the point they meet, but we know the time they meet. So at that point, we can just use the either displacement formula, right? And substitute that time in. So let's say we substitute it into this one here, this displacement here. So if I sub t is 20 here into S of t is 25t take away 0.2t squared. So that means S is going to be 25 lots of 20 minus 0.2 lots of 20 squared. So that will get me 420 meters. And there we are. So that is the displacement, the distance from A here until up to the point where they meet, and that's what they wanted. So there we are. That's the distance for where they overlap or where they meet at the same point. There. Cool. So again, hopefully you're just comfortable what I did there. So again, I want to find the distance where they meet. So that means when two objects are at the same point, again, remember that means their displacements are equal. So what I did here was find the displacement formulas for both objects by integrating from the acceleration or the velocity or whatever, and then I equated their two displacement formulas together, okay, and went from there. Right. Okay, so I've got this question here. Now, I took this question from the constant acceleration mixed exercise. So originally, you are expected to do this by using SUVAT, right? And in general, I do recommend you do SUVAT with constant acceleration problems like this. You'll still get the marks if you use any valid method, that's fine, however you choose. I just recommend doing it that way. But I'm going to show out of interest how you could approach this, use the same problem you've seen before, but using calculus now, right? So I still, as practice, I'd recommend try and do this normally by using Suva. But let's have a look. Okay. So we're told two cars A and B are moving in the same direction on the same horizontal road. At time t0, they're side by side, so they're at the same point, right? At this point O. Car A travels at a constant speed of 30 and car B passes O with speed 20 and has constant acceleration 4. Okay, so it's asking me to work out some information about their journeys, right? Now, I'm not going to jump into A right away. What I'm going to do instead is again, kind of like the last question, just work out the formulas for their velocities, their displacements, and so on, using calculus, right? So, again, we've got two different cars here, two objects, so I'm going to do them separately. So, firstly, car A, right? Now, okay, now what I'm told about car A is it travels with constant speed. So that means the velocity is 30, right? Okay, so that means the velocity is 30. It's this fixed number, right? Because it's constant, okay? So actually the velocity is constant here. So then if I integrate to get the displacement, that means the displacement is going to be the integral of 30 dt, so I'll add a t on, so 30t plus c, right? And that's my displacement, okay, there. Right, but I need to find plus c. But initially, they're at the point O, so they're not travelled anywhere away from O. So actually, the initial displacement is 0, right? So that means when t is 0, s is 0. So that means 0 is 30 lots of 0, add c. Therefore, c is also 0. So that means for A, the displacement function is s of t is 30t. And that's it, okay? There we are. Now for car B, I'm going to do the same. For car B, I'm now told it has constant acceleration. So that means the acceleration function is just 4, okay? It's the constant acceleration of 4. So A is just equal 4. So now I'm going to do the same process of just integrating to get to the other quantities. So if I integrate to velocity firstly, well, v of t, well, 4, the integral of 4, I'll just add a t on, so it's going to be 4t, add d, right? So then I need to find d. Well, actually, I'm told that car B starts at O with speed 20. So that means when t0 initially, v is 20, so therefore 20 is 4 lots of 0 at d, therefore d is 20. So that means my velocity function is 4t at 20 for B. So then to get the displacement for B, I can now integrate, so s of t is now the integral of 4t at 20 dt, and so that'll be 4t squared over 2 at 20t add k, some other constant k, right? So now we need to find k, but again, the same story. Car B also starts from O, so it's not, the initial displacement is 0 because it's at the starting point. So that means when s is 0, t is 0, therefore 0 is going to be 2. If I simplify the fraction, it's 2. So 2t squared, 2 lots of 0 squared, at 20 lots of 0, add k, therefore k is 0. So that means my displacement function specifically is 2t squared at 20t. And that's for B, okay? So now I've worked all that out, okay, it might take a bit long to set that up, but now the question follows quite simply, because now for part A, it wants me to find the speed of B when it's travelled 78 metres from O. Well, actually, that means if it's travelled 78 metres, that means S has to be 78, right? So for part A, if S is 78, then that means 2t squared plus 20t equals 78. Therefore, 2t squared at 20t minus 78 equals 0. So if I solve for t, I get minus 20 plus or minus the root of 20 squared minus 4 lots of 2 lots of minus 78 over 2 lots of 2. So solving that gets me t is 3 or t is minus 13. But of course you can't have that solution because it's negative. So t is equal to 3. Okay. And there we are. Now that's the time, but it wants me to find the speed when it's at that distance. So now I know the time, I can substitute that into the velocity function. So v of t when t is 3. So therefore v is going to equal, well, v is here. For b, the, where was it? The velocity is here, 4t at 20. So it's going to be 4 lots of 3 at 20. So that's going to be 32. And there we are. And then for part B, it's asking me to work out the distance from the starting point O of A, of car A, when B is at this distance. So it's going to be at the same point in time, right? So the same point in time is when t is 3. But I want to find the distance of A. But I know the distance formula for A is it's 30t here. So for part B, simply I'm going to sub in t is 3. Right, so I'm going to sub t is 3 into S. So that means S is going to equal 30t here, because I'm considering car A now. So this is car A's displacement formula. So after 3 seconds, it's 30 lots of 3, which is 90. There we are. Then for part C, it wants me to find the time when B overtakes A. So if you imagine at the point where the cars are overtaken, they're going to be at the same point then, aren't they? So that means, again, the displacements are equal. So they overtake when the displacements are equal. So the displacement of car A is equal to the displacement of car B. So therefore, well, the displacement of car A is again 30t. So 30t is equal to the displacement of B, which is here, 2t squared at 20t. So then if we solve that, we get 2t squared minus 10t equals 0. So therefore 2t of t minus 5 equals 0. So t is 0 or t is 5. But clearly when they overtake, it's going to have to be the latter time of t is 5. So t greater than 0, so t equals 5. So there we are. So yes, the setup might have been a bit long to find out all the functions for the velocity and the displacement. But actually, once you get that set up and you got all the functions, you can quickly work out the information they want. Okay, and that was 9 marks worth there. So yeah. But yeah, I thought that'd be quite an interesting angle we can take to solve these problems.